We're going to spend 2 days on spectroscopy, and might as well start with Robert. What is spectroscopy?
It's the interaction between some sample and some radioactive stuff or something.
Well, we're talking about spectroscopy. Think about it.
Matrix or satellite.
Do you want to analyze and have an interaction between your matrix? Think about it. Anybody? Spectroscopy is the interaction between radiation and matter, right? Yeah. And you can say radiation, but radiation is too broad. You should probably say what? Electromagnetic radiation. You could say that, or you could say there's an L. Light, right? But either one works. Whoop. Okay. Light acts like a wave, other times a particle. I added this stuff this morning. That's why I was a little late. Ashley, what does this represent? Magnetic waves? Probably a better word than that. Magnetic what? Notice how the lines are really close together. It's this, what I'm after, is stronger. Now it's weaker, because look at how they're spaced out. What is? What's stronger? What's weaker? She was halfway there with magnetic. Field. A field. Right, a magnetic field. Okay. What is this? Now these things are disappearing now that, you may have seen this, but your kids are never going to see this.
What is it? If it's an antenna, judging by how does this antenna work?
Yeah, but where did you see it? On your TVs, right? You can rotate the loop back and forth or different directions and things, right? So there's two types of fields we're going to be talking about, magnetic and what's the other one? Well, let's not worry about the other one. Let's stick to magnetic. This is a magnetic antenna. Okay. Well, how does it work? Right? Here's all the physics of it. Or you could do the "Are you smarter than a third grader" way. Right? What is the guy holding? Magnet, right? It's just a magnet that's bent in the shape of a horseshoe, right? And the dude's, what is this thing? What's the black thing? A wire, right? So the technical word is oscillating. He's oscillating that magnetic field, going across the wire, back and forth, back and forth, back and forth, back and forth. And he's inducing a current. If you have a magnetic field that's moving or oscillating, right, changing, its strength, what is the strength? Right here, right? Number of lines per unit centimeter or something, whatever you want to talk about, right? You can induce a current. And that's what's going on here. This antenna is made out of metal. Magnetic field must be oscillating. The TV station, that magnetic field must be oscillating. If it wasn't, you're not going to induce a current. Okay? And then you pick it up and you get your signal. Another antenna. Straight up and down pole. Metal. Or you can see it here. What type of field is this thing talking about? Electric field. All right. Over here. What did I show? I've shown this to so many classes and I can't keep straight which ones. Who's seen this thing before? Okay, Alice. Randy, you seen it? What did it do? What was it for? Demonstrate what? What's that? Okay, here's a fluorescent tube. All it is it's evacuated, and there's some small pressure of argon in there. And then this white powder is just fluorescent. If a gas, or any gas molecule, they just use argon because it's heavy and it stays in there, right? It strikes that white fluorescent stuff, it emits Roygbiv. That's why they picked this white powder, because they don't want it to glow red. They want it to be white, right? But how does it? What makes it oscillate? Or what makes those argon things move? An electric field. And just imagine those number of lines per unit millimeter or whatever. It's going to be really concentrated at the end, right? It's just an extremely high voltage. In fact, you can hear it, hear the snapping. Maybe you can even see the purple stuff. That's the plasma, the fourth state of matter, but you can hear the sound. What's the sound coming from? Air is physically being torn apart. Air is a great insulator. But this is such a high potential, it's tearing the air apart. And when the air gets, well, air has to go back together. Bam! That's the sound. Right? That's what thunder is. But if I get this close enough, this electric field, the lines can actually start exciting forcing those argon ions to move. Now, charge can only push charge, plus minus. It's that simple. Plus pushes minus, minus pushes plus. Does argon have a charge? When you think of argon, don't you think of like a sphere? A little argon atom? There's no point for it to have any shape or charge, but it has to. How? How can argon have a charge? Nope. Not at all. Nope, not at all. Hmm?
Did they give it a charge? When they put it in there?
No, because it would lose it, right? It's argon, noble gas. And plus, the only way for something to keep a charge is to have the opposite with it, magnesium chloride. You have to have magnesium ions and chloride anions. That's the only way to keep them, and they don't even really keep their charge. I mean, everything's shared, and you got this. What was the van der Waals? London forces. What was that? Intermolecular forces. How'd that work? Was it really strong or really weak? Really weak. Well, why did we talk about it? It had to do with what? It would work better for big molecules. Well, why did we talk about it? Otherwise, these big molecules couldn't form a what without this concept? Well, the bond is too strong of a word. Intermolecular force, just an interaction. Without them, they wouldn't come together and form a, there's an L. Oh, Li. Q. Liquid, right? There's no reason for them to stick together. Okay? But it's this big-ass molecule, right? Who cares, big-ass molecule? Go smaller. Something that doesn't have a dipole. No HCl stuff going on, right? Oxygen, O2. Same thing. There's no if you say there's a dipole on it, I'll kick your butt, right? Because it's the exact same atom. There's no way it can have a dipole. Or talk about argon, whatever. You can make argon liquid. You can make oxygen liquid. You have to really make it cold because the intermolecular forces are so weak. All that's there is van der Waals. But what is van der Waals? That's what I'm driving at. What is it? Yes, it's an attraction, but why? For our yeah, they stick together. For our understanding of how things work, we can't get away from the dipole idea. Because that's all we have to work with. That's all our theories have to work with. So what's in dipole? Electrons spend more time on one side than the other. That's all it is, right? Now, usually, if it's a permanent dipole, it's because of electronegativity. But if there is no electronegativity difference, what could cause electrons to hang out on one side more than another? Now, it might only last a femtosecond, which it does. bam, a bam, a collision, right? A collision. A collision is going to cause these guys to go to one side or the other. Yeah, argon is really, really, dilute in there, but they're colliding with walls and things. Instantaneous dipoles, very, very brief moment in time. Those are the only dudes who are going to interact with this. Everything else can't even feel it, doesn't have a charge, right? So that's kind of what's going on there. Okay, so that was kind of a side view, but here's an antenna, and this is working with the what type of field? Electric field, right? Now this antenna is emitting or collecting? It's emitting, right? Antennas can do that. You just have to oscillate, right, and oscillate the current up and down. So a moving charge emits an electric field. What's the moving charge? Just electrons. That's a radio tower, right? It's a little walkie-talkie that's sending a signal to whoever, Joe. Okay. All right. So this is what type of antenna? The little vertical one. I lost here. It works on what type of field? Electric field antenna, right? Okay. Now I can't let you go without talking about this. Centimeter. What do I have something against? I didn't bring it. And I really think they're going to cause cancer. Cell phones, right? Now what is this? Centimeter, what does that have to do with anything? That's the wavelength of with an M, the region of electromagnetic spectrum that cell phones work on. Microwaves, right? Look at the intensity of the microwaves and the signals. Here's an antenna, right? And it's much larger around the little antenna guy. So this is just focused down, and so you have your little cell phone in your pocket. May not be the best place for it. Purse might be a lot better idea, right? Because look at this. It's right next to your body. Do microwaves interact with your body? Stick your head in the microwave and you'll find out, right? Microwave oven? Dang right. So much money into the cell phones and things that it's politically incorrect, but it's just like football in Texas, man. There's a problem and no one's talking about it. Right? That's how it is. Okay, I think we got all this stuff. Electromagnetic as a wave. Be able to reproduce this diagram of plane polarized radiation. Okay, so it looks like the blue is the electric field, B is the magnetic field. Okay, so you have these, just like before, the strength is the number of lines. So the strength is oscillating, right? Now you already have it sketched in there, so I don't need to give you time to do it. But which direction is the wave moving? Is it moving? It has to be moving, right? Which direction? Where's it going? Right, left, up, down. Where's it going? Everywhere? Because where's the motion? Because waves have a motion, right? Like water waves, up and down. Okay. This guy has a motion too. Up and down here, right? And up and down here, up and down this way. They're perpendicular to one another, right? But the whole thing is moving in which direction? Physically, yeah. It's either moving, I don't know, it's either moving this way or it's moving that way, the other way. I'm not sure which direction, but right? It depends on where the source is. You just have a little, have your little antenna thing over here, something that's emitting the electromagnetic wave, right? So then it'd be going that way, okay? And it's plane polarized because the electric field is all in one plane. The magnetic field is all in one plane. That's what plane polarized is. Is the light coming from the projector plane polarized? Or off this screen plane polarized? Well, you could check. use starts with a P, polarizer. Okay. Now first let's figure out what a polarizer is. This just lets light through that's in one plane. Now I'm not sure if it's if the electric field is this way or if it's that way, because this thing's not marked. But that's how it is. It's either letting all electric field this way. And you just focus on the electric field. It's a lot easier just to stick to one thing. And plus, we'll see why in a little bit. But all right. So if the light coming from this flashlight was polarized, it would all disappear. Now, this is something only quantum mechanics can describe. Why the intensity goes down exactly 50%, but we'll leave it for them. However, if I get... No, think about it. Think about it, Robert. Robert, you're missing the point. You're missing the point. You have black body emitter, technical word, right? But the radiation is emitted in all directions. Every single direction, right? This electric field is. So why, if I only let it out in this direction, it should be extremely dim, shouldn't it? It should be extremely dim. But yet it's exactly 50%. Makes no bloody sense. All right? Do you see why it doesn't make? Do you see that? Because it's emitted in all. This guy is emitted in all directions, not just this one, but all of them. Right? So you put it in here. It should be very dim, but it's exactly 50%. Okay, but now we know all the light is emitted. Just pick a direction. So all the electric field's in this plane, or the plane of the table, one of the two. Right? I put another one in front. Well, if I line them up, nothing happens. But if I go, how many degrees? 90. Across the polarizers, nothing's going to get through. Okay? So it is polarized. This does make sense, and it works. Okay. A wavelength. Circle a wavelength. Circle a wavelength. Tell me when to stop. I'm going to start my circle here. Where do I stop? Alice, where do I stop? Keep going. Keep going. Right there. Perfect. See? It just has to be one part where you can cut it and paste. It's going to be the exact same thing over and over and over and over again. Because if you just cut it right here, it's not going to work. All right? It's only half of a wavelength. Okay, so that would be a wavelength. How about the amplitude? How would you describe the amplitude, Kathleen? Yeah, like the top of the peak to the midline, right? And you can go either talk about the electric field or the magnetic field, but why specifically is this guy polarized? Anna, why would you say that this thing is polarized? If I said draw a plane polarized radiation, you have to draw something like that. What's so special about it? The hint is plane. Anybody help her? What's that?
Is it because it's one plane?
Yeah. Well, what is the it? You're so close. The pick one. The either pick the blue guy or the red guy. The electric field is all in the same plane. Now you can say the magnetic field is all in the same plane too, but folks, spectroscopists talk about the electric field much more often. How can we make plane polarized radiation? Rob, how can we make plane polarized radiation? Yeah, use a little polarizer would be one way, right? That'd be one way. There's plane polarized radiation. There's an easier way. Glare. What's glare? Let's see if this works. Oh, yeah. Okay, what's glare? Glare is polarized radiation, right? These are my Babe Winkleman sunglasses. And they are...
Dorky.
No, they're not dorky. They're polarized, right? Who's Babe Winkleman? You got to be up north to know this, and you should know who Babe Winkleman is.
Yeah, sounds like a dork.
He's a fisherman, big-time fisherman. He's got his own TV show, okay? And so why would fishermen want to wear polarized sunglasses?
Sit on the sun all day.
There's a lot of what?
Radiation from the sun.
A lot of the G word.
A lot of glare.
From what? From the
Lake.
lake. Because if you don't have polarized sunglasses, you can't see the little what in the water? The little fishies, right? So you got to have polarized sunglasses. Okay, that's just how it is. So it removes the glare. Now, where is the glare, right? If I'm looking right here, I'm looking at the table, I can see kind of, depends on where you're sitting. Don't you see, like, off of John's shirt, you see a white reflection, right? If you put on the polarized sunglasses, it disappears. I can get the glare back by moving my head exactly what? 90 degrees. There it is. Okay? So the polarized radiation is polarized in the plane of the water or the table. That's the glare. So that means these guys must be polarized in this direction to block it. Okay? You can try it. What is glare? It is polarized radiation. Well, it's really technical to make it a whole sentence, a whole story. Glare would be, unpolarized radiation striking something flat, right, and reflecting. Like in the road, you see a lot of glare in the road or off of other cars. So polarized sunglasses are a nice idea. No. Now okay. How about these things? Real 3D.
You stole those from a movie theater.
Real 3D. Real 3D. What do these have to do with polarization? Yeah, you have to kind of look at the table. Look at the table. You have to kind of see the table. Now, it might be easier with the lights on. Let me try the glasses. Let's see if it's easier with the lights on. Then we'll talk about the 3D glasses. I think it's harder with the... No, it works. It's easier with the lights on. So you pretty much to notice the glare, you have to be interactive. You have to move your head 90 degrees. Look at the table, rotate your head 90 degrees, go back, and you're going to see glare big time. You're just so used to seeing glare that you don't think about it. Okay? So you have to do this several times. Prove it to me. Right? Okay. What's so special about these 3D glasses? How do they work? All right, you take them off, the screen looks funky.
Yeah.
Does anybody know?
I just started playing with them. They're polarized.
Take a polarizer. No effect really on this one, so they must be what? Aligned, right? Okay. Make sense? I got to make sure I'm doing this right here. Oh, they're not. That is curious. Okay, I thought they were exactly out of alignment by 90 degrees, but they're not. All right, if you rotate it,
Yeah,
it's not quite 90 degrees. Right? They're playing around with polarity. And they're not completely polarized either. They're only partially polarized. So something complicated is going on there to get some kind of depth perception. Okay. What's an electric field? We kind of talked about it, right? It's kind of this idea, but think of that device that creates a huge voltage, right? And what is a volt? Yeah, its units are volts for electric field. What's a volt? A volt is what per what? Joule. Good. Joule per close. Joule per coulomb. And what is joule? Joule is a unit of energy. So it's really energy per unit, what's coulomb? Charge. It's energy per unit charge. So a huge voltage, right, can really make a charge fly, right? Because it's energy per unit charge. Which field interacts with matter for most types of spectroscopy? Which one would you guess, John? Not magnetic, electric. Yeah, electric. Okay. The FTIR, talking about oscillating dipoles, and we'll get to that. UV vis, electronic transitions. Almost all these types of spectroscopy deal with the electric field. Which field interacts with matter, Emily, with NMR spectroscopy? Yeah, it's deduction, right? It's got to be magnetic, otherwise I wouldn't bring it up. What is the difference between monochromatic, Sandy, and polychromatic light? One what? One what? Monochromatic means one, but one what? One. Now, if you want to talk about the electromagnetic radiation we can see, you could say one. Starts with a C. Red.
Color.
One color, right? If you want to talk about the electromagnetic radiation we can see, one color. Polychromatic would be, yeah, many colors. So it might be better to say wavelength, though. Monochromatic, one wavelength. Polychromatic, multiple wavelengths. Then it doesn't matter whether you can see it or not. Electromagnetic spectrum. Let's start with this energy idea. Ricky, let's start with low energy. This side. Does that refer to low or high frequency if you have low energy?
I'm going to say high frequency.
I'll give you a hint.
No, just I think.
E equals h nu. That's the energy of a photon.
Okay, so.
Equals Planck's constant times the frequency.
Oh, okay. Well, then it's going to be low energy, low frequency.
Exactly. Low energy, low frequency. Low energy, low frequency. How about wavelength? Pablo, I'll give you a hint.
That's what I was thinking.
So you don't have to guess. If you know what the symbols are, you'll be okay.
What's the bottom?
Lambda.
Okay.
The energy of a photon equals Planck's constant times the speed of light all over its wavelength. Low energy would be, yeah, really, really, well, high. Long might be more descriptive, right? But high wavelength. Okay, so that means that high energy just must be the opposite. High frequency, right? Really short wavelengths. So let's throw some stuff on here, Adriana. The electromagnetic spectrum. Give me a region and tell me where to stick it.
Be nice.
We're on the radio. Well, not the radio. We're on.
Well, there's a hint.
Yeah, so a region of it. Yeah, and just tell me a region of the electromagnetic spectrum. No, just give me a type of light. Because the whole thing is light. What's ultraviolet? Okay, where do you want to put it? On the higher energy side, because ultraviolet light can give you what? Yeah, sunburn, right? So let's throw UV in here. I don't know. UV's right here. Why not? I have no idea, right? Just put it in there. There's no numbers in here. Alice, another one. There's UV. Now we can actually give a wrong answer by putting on the wrong side of the UV. Because Adriana couldn't be wrong. There's no place to put it. Okay, The light that you can see. So, and what's the name of the dude? Nobody names their kid this anymore. Roygbiv. But so we could write Roygbiv, but let's just write visible instead. So where would you put it though? Yeah, lower energy. Okay, visible. Okay. Now let's ask the question, Roygbiv, Ashley. Should we write Roygbiv, or should we write? Let's see. How do you say that backwards? Vib. Oyer? Which one do you write? So the question really is, just pick one. Like R stands for red. So should red be the lowest energy you can see, or is red the highest energy you can see?
Lowest.
Oh, stick to V. V would be easier. Yeah, because ultraviolet, right? So V, violet, is the highest energy. So it is. So Roygbiv will work just as said. Okay. Keep going, Kathleen. Okay, where would you put them? Very low. Okay. Would it go right after? Is there something? So this is radio down here, but I don't wanna. Okay, Anna. Another one. X-ray. Okay. Where would they go? They can go through skin, but not bone. You're only supposed to get so many. When they push that button, they go running around the wall, right? So high energy, right? X-ray. Robert.
Guessing. Infrared.
Where? After UV? Infrared. There you go. Infrared. All right. Can't see it, but they have those little nighttime vision glasses, right? You can see the little dude's footsteps in the dark. John. A few more common ones. That's why I keep going, because you've heard of more.
Starts with a G. God.
Gamma, okay. Stuff from space. Yeah, where would you put it, though?
Oh, I was like, I was writing the red.
They're really worried about this stuff. Especially the astronauts.
Yeah, after the UV.
It's even further out.
It's like the scariest radiation.
Yeah. Okay, I say one more. One more. Microwave. You can cook hot dogs, make
I'm
popcorn.
thinking it's in that bowl that you conveniently left.
On the left.
Actually, I screwed up.
Yeah.
Where does microwaves go?
Um,
Yeah, between radio and infrared.
That's what I was thinking.
Let's just squeeze it in.
Oh, look. I had it again.
Now, how the heck can that be, Emily? How can something that can make your head blow up or cook hot dogs or whatever be less energy than less energy? Now, what is infrared? Yeah, than your remote control. Infrared is also more common word. There's an H. Heat. Oh, Emily. Sorry, Emily. You're getting off. Emily. Okay. So, Emily, how can this be? No, heat. We already answered it. But how can it be that microwaves are less energetic than heat? Less energetic than your remote control. But yet you can cook hot dogs. How does that work? Does anybody know?
The big wavelengths. Yeah.
No, they're only like a centimeter. Yeah, they are. They're like about a centimeter, right? Right. This visible stuff is nanometers, right? This stuff is micrometers. This stuff is meters. Right. How does it work? Here's a hint. Infrared's are micrometers. That's a mu symbol, 10 to the negative 6, like a hair, pretty much the width of a hair. I'll give you a hint. If popcorn didn't have water in it, it won't pop. If the shell has a little hole in it, right, the steam's going to escape and it won't pop. You get an Old Maid. Okay, well, that's a hint, but I don't know if it's not a strong one. It has to have what? It has to have water. So what's so special about microwaves and water? Well,
Transfer energy.
yeah. Microwaves exactly match the energy necessary to make this dude do what? And do it faster. Not vibrate. Vibrate is what region? Vibrational energy. Vibration is higher energy. Vibration is IR. This is a weaker energy interaction. What could that guy do and to be weaker than vibrating? Than making bonds stretch? What else could that molecule do? It could rotate. It makes water rotate. This is what's very, very weird about our microscopic world. All these different little motions are quantized. To make water rotate, it's only the microwave energy that it can absorb. That's it. No, it's got holes in it. Right by the door where you grab it.
That's scary. He's not kidding.
All right? I've got, right? You're the only one who's seen it.
Yeah.
I've got my little microwave detector right by the door. It's pretty cool though.
It's scary though.
Yeah.
Yeah, just don't
Yeah.
wash your stuff good.
Alrighty. So that's it. That's day 2 now.
Why can you see infrared with a cell phone camera?
Why can you see infrared with a cell phone camera? How can you see infrared with a cell phone camera?
If you take your cell phone and you turn on your camera and you point it at the end of a remote and you hit the button, you can see the light turn on inside the remote.
Oh yeah.
That's how.
Really?
Yeah, that's how Al-Qaeda operatives see American troops because they have infrared lasers on their phone, and they just hold up the cell phone.
Hold on. Hit the. Let's stop this here. Hit the lights.